In today's class, basically we will go with different applications of operational amplifier. So in this series we will just go with a multiplier amplifier, like how we can implement a multiplier circuit by using operational amplifiers, and also we will see the logarithmic amplifier. So here in logarithmic amplifier the output will be the log of the input. So these type of application of operational amplifiers we will be seeing into this class. So we will start with the multiplier circuit. So a multiplier circuit is like we have an input and we are getting some output. So this is a circuit, that is a multiplier circuit. Here we will be providing an input and we will get an output. So output will be such that V output should be such that a multiplier should be there, that means a constant will be there multiplied by the input. So that means here the term A can be considered as a multiplier term. It will be a constant. So the output will be a multiplier constant or constant multiplier with an input. So similar structure we have already seen in the basic operational amplifier. So in basic amplifier this is the circuit. So in this basic amplifier we have seen it is the input we are providing is at the inverting terminal. So the output in this respect will be, so output will be the minus Rf by R1 into input, that is V1. So this will be the output in case of inverting type of basic operational amplifier. So here again we can just see, so the output that we are getting is a multiplier with input. Output is having a multiplier with an input. So multiplier here is a negative value. Okay, so suppose this is a gain, so this multiplier is, we call it a gain with a voltage. So it is a type of multiplier circuit. It is having a constant multiplied by the input. So similar concept we will use to implement the multiplier circuit. So the multiplier circuit that we are going to implement is fixed gain inverting multiplier. So inverting multiplier, we are going to apply the input at the inverting terminal. The similar structure is there. So the only difference here is we are connecting a resistance RC to the non-inverting terminal. So this RC is basically connected to reduce any offset current. So offset current is basically once an operational amplifier is there, and the ideal operational amplifier should be like whatever the input is there. Suppose we are connecting the input and this input is 0. If input is 0, the output should be 0. This is the case of ideal case. But practically, even if the input is 0, V output is not equals to 0. It is having some value. This is the practical case. So to make sure like our output is 0 when input voltage is 0, we need some resistance connected to this way. So why it is so, like initially we have assumed like the current inside this operational amplifier is 0. We have assumed it like the current is 0. I1 and I2 are 0. Okay, this is the ideal case. But in practical, when I1 is not equals to I2 is not equals to 0, then there exists an offset current. Offset current means if the current should be 0 but current is not 0, so there will be some offset current. So when there will be some current flowing through this terminal, so the voltage at this point we need to make sure like Vn is equals to Vp. So to make this equal, we need to connect a resistance so that whatever the voltage drop would be here, similar voltage drop would occur here also. So that's why there is a resistance used for practical circuits. We need to implement by using resistance connected to the non-inverting terminal. So this is overall the circuit of fixed gain inverting multiplier. So in this case, the output that we will be getting is the similar way. It is a non-inverting case, it is an inverting case. So it is an inverting case, but that means whatever the input we are applying, that will be an inverted output. Okay, so similar to that, it will be Rf by R1 and multiplied by the V input. So this will be the output, and that output will be replicating like it is a constant multiplied by input voltage, and this constant is equals to minus Rf by R1. This is our multiplier, or you can call it constant multiplier. So it is very easy, simple, similar to the basic operational amplifier we have seen. So it can be represented in terms of fixed gain inverting amplifier. Okay, so this A here is constant multiplier, or we can call it a gain also. It is a gain. Okay, so next we can see fixed gain non-inverting amplifier. Okay, so in the previous case it was inverting amplifier, so the similar multiplier we can implement by using the non-inverting also. So the non-inverting case we have already seen. So the input we will be providing at the non-inverting terminal, and the inverting terminal will be part of the feedback. So in that case, the output will be given by 1 plus Rf by R1 multiplied by the input. So here this will be our gain. Suppose it is A, then again the V output will be A multiplied by the input. So this is a non-inverting amplifier. Next is a multi-stage gain multiplier. So multi-stage is, that means we can use multiple stages of operational amplifiers to implement the multiplier circuit. Okay, so suppose this one is V01 and this is V02 and this is V0, final V0. So in this case, the final V0 that we will be getting is, that will be the we will be getting is it will be the it is, suppose this one is gain, this is gain of 1 or A1 we can just write. So suppose it is gain A1 for first amplifier, A2 and A3. So there are three different operational amplifiers and it is having three different gains. So for each operational amplifier there will be an there will be a individual gain. So the output, that final output that we will be getting is, that will be the multiplication of individual gains and the input. So from there we can just see, we can design a multiplier circuit with multiple stages and its gain will be, so this will be the gain, or multiplier, a constant multiplier will be there. So the constant multiplier here implemented by three different stages. So A1 multiplied by A2 multiplied by A3 will be overall the gain of the circuit. Okay, so this, how this can be implemented we can just see. So this is one of the inverting amplifier. So V01 here, if we find out the V01, so V01 will be it is an inverting amplifier. So here the feedback is connected to inverting terminal, and the input is connected to non-inverting terminal. So if input is connected to non-inverting terminal, the output will be with respect to the non-inverting case. So it will be 1 plus Rf by R1 multiplied by the V inputs. So this will be the V01. In the second case, if we want to find out V02, so V02 will be, again we are having a feedback, okay, to the non-inverting side, and the input that we are connecting. So here V01 now acts as the input, and it is connected to inverting terminal. So if it is connected to inverting terminal, that means its output will be minus Rf by R2. So Rf by R2, this resistance, multiplied by the input that is here V01. The next final output that we can get, V output, will be again here it is an input, that is V02 will be behaving like an input, and it is connected to inverting terminal. So if it is connected to inverting terminal, its output will be minus Rf by the resistance, this is R3, multiplied by V02. Okay, so finally by putting all these values, we can get the output voltage. So output voltage will be minus Rf by R3 multiplied by V02. So V02 is this one. So we'll just put the value of V02. So it is minus Rf by R2 into V01. So V01 is there. So V01 is given by here. So we will be writing V01. So V01 is 1 plus Rf by R1 into V input. So from there we can just see the gains. So the individual gains are this one. So this is the A1, or it is the A3 gain of this one. This Rf by R2 is the gain of second stage, and this is the gain of first stage. So again we can just see the output is the individual gain multiplication with the input. Okay, so individual gains are multiplied and with the input terminal. So with respect to that, we are getting a multi-stage fixed gain amplifier. Okay, so this is amplifier where we are multiplying the input with a constant gain. So this constant gain will be decided based on the value of R1 Rf, R2 Rf, and R3 Rf. So that will be deciding the resistance values, will be deciding the gain. So whatever gain we are requiring, based on that we will be writing this resistance values. So this is how we can implement the multiplier circuit. Okay, so next is another case of multiplier. So the similar case of multiplier is a voltage buffer. So here it is called voltage buffer, or it is called voltage follower, or it is called unity gain multiplier. So we have seen the multiplier above, so that is having a fixed gain. So in this case, if the multiplier is having unity gain, that will be called as voltage buffer or unity gain multiplier or voltage follower. So this is implemented by making sure like the gain is, so here gain is equals to 1, then the circuit will become unity gain. It is unity gain multiplier. So unity gain multiplier means it is the gain where gain is equals to 1. So the circuit will be this. So here we are not connecting any resistance. So whatever the inverting terminal is there, inverting terminal is directly connected to this output. So this is how we can implement, and the input will be connected to the non-inverting terminal. So with respect to that, so once there is no resistance, okay, so the output that we will be getting is having same as the input. Okay, so output in this case is given by V input itself. So when output is equals to V input, that means it is having a gain of 1. So when it is having a gain of 1, that means it is having a unity gain multiplier type circuit is there. And it is also called voltage follower, means whatever the input is given, the similar is the output, that's why it is called voltage follower. And it is used for voltage buffer. Buffer means, so any circuit is there, suppose any black box is there, so the property of a buffer circuit should be like its input resistance should be very high, okay, R input should be very high, and output resistance, if we talk about the output resistance, its output resistance should be 0. So here input resistance should be infinity and output resistance should be 0. This is the property of buffer circuit. This is we have already seen in the previous classes also, like how the effect of R input and R output will be there on the loading of the circuit. So basically, to avoid the loading effect, we use the buffer circuit. So it can handle like whatever input we are providing. So suppose we are providing input voltage with a resistance, suppose some RS resistance is there. So whatever input we are providing, if R input is infinity, all the voltage will be appearing across the R input. So that means whatever the input we will be providing to the circuit, it will be taking the complete input voltage, and output resistance is 0. So whatever output it will be providing, that will be across the load. So if there is a load resistance, the total output will be total output voltage will be across the load only. There will be no voltage drop across the output resistance. So this is the property of a buffer circuit. So that's why the use of operational amplifier can be done to implement the buffer circuit. So this is the connection that how should be making, and here the gain should be 1. So if gain is 1, the output will be directly proportional to the input, okay, with a constant gain, that is 1. So next is the use of buffer circuit to provide different output signals. So input signal is there, V1 or V input, suppose it is an input signal, and if we want to have different output with respect to this input, so we can implement two different voltage follower or buffer circuits. So these buffer circuits will be providing the output that will be different. That means these two outputs will not be depending on each other. That means there will be no relation between this. But suppose if we take the output directly from suppose this is the circuit, and if we are taking the output here also, this is V1 and this is V2. So whenever we are connecting a load to here, and if we are connecting a load here, so this is RL1 and this is RL2. If we are connected to two different loads, it will be affecting the output voltage. That means the V output 1 and V output 2 will not be constant now. It will be different. Okay. So to avoid this problem, this is loading effect. Basically, if two loads are connected at the same terminal, there will be a loading effect. So to avoid loading effect, we use two different buffers, and these buffers now are able to handle the load resistance because it is having output resistance that is 0. So output resistance is 0, so it can handle the load without having the loading effect. Okay. So this is how the buffer circuits can be used to implement a different type of output signals, okay, based on a single input signal. So the next part we will see is logarithmic amplifiers. So logarithmic amplifiers can be implemented by using the operational amplifier with the help of a diode. Okay, so instead of using a resistance or capacitor, we are going to use a diode, because in logarithmic amplifiers, the output that we should be getting should be a constant along with log of the input. So this is how we should be calculating the log of the input, and output should be the log of the input. Okay, so log here is, it could be log of base 10 or log of base e. So here for implementing with the diode circuit, it is like we know the current equation in case of diodes. So this current equation of the diode can be implemented to use as as a logarithmic amplifier here. So the pattern of input and output, or the relation between input and output, should be in log with the input, the output should be there. So in the similar analysis, but we have gone with the resistance case. Similar analysis we can do here again. So if it is an operational amplifier, that is an ideal one. So in that case, so there will be a virtual ground or virtual short will be there. So if it is ground, it will be also ground. So if it is ground, there will be no current flowing inside. So we are considering like the whatever current is flowing here, the same current will be flowing here. So by using KCL, we will be saying like input current will be equals to the IF current, that is diode forward current. Okay, so here input current will be, this is the direction, that means V input minus 0, V input minus 0 divided by R1 will be equals to IF. IF will be the current that is flowing through this diode. Okay, so that is the current that is flowing through this diode. So diode current is basically how we know the diode current equation. When diode is forward bias, okay, so if the diode is forward bias, the diode current is given by, in forward bias case, the diode current IT is given by I naught, that is the leakage current or reverse saturation current that is there. Okay, so I naught multiplied by e to the power whatever the forward voltage of the diode is there, Vf divided by NVT minus 1. Okay, so this is the diode forward current. We have gone through in the previous classes, you can just see that. So this is a basic equation of diode current. So now if the diode is forward bias, we will be implementing the same current, this one, to here. So input current is this and IF will be this one. So IF we will be implementing is I naught into e to the power Vf, that is forward voltage of diode, divided by NVT minus 1. But here we can see the diode voltage is this one. So this one is connected to 0 and this terminal is connected to output. So here Vf will be equals to, like, if this is positive, okay, that means this is the positive voltage. Okay, this is at high voltage and this is at lower voltage. So it will be Vf will be 0 minus V output. So from there we can implement the Vf will be equals to 0 minus V output. So now we can just put the value. So V input divided by R1 will be equals to I naught e to the power, we will be, instead of Vf we will be writing minus V naught minus, or V out divided by neta Vt minus 1. Okay, so this is the basic from the basic analysis how operational amplifiers we have analyzed. The similar steps are there also. So now once we have obtained this expression, now we can proceed with separating the output from the input. Okay, so to separate it out, we will be just multiplying here first. So we can just multiply, and or we can just separate it out, like we will be dividing it here further. So it will be V input by R1 I naught e to the power minus V out divided by neta Vt minus, it will be multiplied like I naught, again multiplied. Okay, so now we will be further separating it, like I naught e to the power minus V out divided by neta Vt is equals to I naught plus V in divided by R1, or we can further like e to the power minus V out divided by neta Vt is equals to I naught, we will be dividing, so it will be 1 plus V input divided by I naught R1. So now we will be taking log to both the sides. If we are going to take log on both the sides, we can just get like minus V out divided by neta Vt is equals to, and log to the base e if we will taking, so this will be the output, so it is log to the base e 1 plus V in divided by I naught R1. So this is by taking log on both sides. Okay, so now we can get like minus V output will be equals to neta Vt log to the base e 1 plus V input I naught R1. Or if we reduce this minus sign, we can get V output is equals to minus neta Vt. This is the output that we will be getting. So once we have got the output, we can just see from the output like the output is in relation with the log of the input. There are some other parameters are there, but in final conclusion we can just see it is the log of input is the output voltage. This is the relation. One more point we can consider, just like just to simplify this expression. So consider if in the case of diode, the I naught that is called saturation current. Okay, IS or I naught we call it. So it is the saturation current or reverse saturation current that is flowing. So it is reverse saturation current. Okay, so I naught is reverse saturation current, and its magnitude is in nanoamperes are there. It is in nanoamperes. So that means it is very, that means I naught is very small. Okay, it is very small. So if I naught is very small, then V in divided by I naught R1 will be very greater than 1. At least it will be very greater than 1 itself. Okay, so when it is very greater than 1, we can just simplify the above expression by putting like V output will be equals to minus neta times Vt log to the base e. Instead of 1 plus something, it is very greater than 1, then we will be neglecting this 1, so it will be Vn divided by I naught R1. Okay, so this is the simplified one. This is how we can implement the concept of logarithmic amplifier. Okay, or the log of the input is the output. So by using the diode circuit, similar circuit we can use by using the BJT also, because in BJT also we know the current flows is equals to the diode current itself. So there will be the relation of log or e to the power forward voltage, that is forward voltage on the input side, that is VBE is there. So that BJT can be also used for implementing the logarithmic circuit. So the next point we will see is anti-log circuit or anti-log amplifier. So in anti-log amplifier we will use the similar concept, but here the diode that we are using as a feedback, we will be using the diode as the input side, and the resistance will be used on the feedback path. So this is how the anti-log is there. So anti-log tells us like whatever we are going to have, so log we take is, if it is written in the power of e to the power, we are representing it in linear type of relation. Okay, but in anti-log it is just opposite to the logarithmic amplifier. So here that's why it is we are just replacing the diode circuit and the circuit of antilog we can implement. So here also we will be writing like so by using the virtual ground concept. This we can get, and also I1 and I2 the current inside the op-amp will be 0 as our input is considered as infinity. So if this is the case, now we can proceed with the KCL. By KCL, IF will be equals to IR. So IF will be the forward current. So forward current will be I naught e to the power the diode voltage, that is Vf divided by neta Vt minus 1 will be equals to this current across this R1. So it is flowing from this terminal to this terminal. This is the direction. So 0 to V output is flowing. So 0 is higher and V out is at lower voltage. So it is higher minus lower divided by the resistance, that is R1. So this is how we will be getting the relation in terms of the current expression. But here again we can see the forward voltage of diode is this voltage minus this voltage. So this voltage is input voltage minus this terminal, that is the terminal that is connected to Vn. So that is 0. So it is forward voltage is nothing but the V input still. So now just we will be putting the value of forward voltage here. So it will be V input divided by neta Vt, and it is minus 1 is equals to minus V output divided by R1. Now we need to get the output. So we will be separating it out like V output is equals to minus I naught R1 into e to the power V input neta Vt minus 1. Okay, so this is the expression that we have got with respect to the circuit that we have got. Okay, so in this case we can just see, so if we want to find out, it is like e to the power V in neta Vt is there minus 1. Okay, so similar expression we can see. So this term, because V input is positive, when V input is positive, so e to the power this one term will be very greater than 1. So we will be just neglecting this term. We can write, so it is I naught R1, it will remaining is like e to the power V input divided by neta Vt. So we will be neglecting this minus 1 term. So this is the expression. We need to implement it in terms of antilog. So if we want to implement it in antilog, we can just write like this is an approximate one. So minus I naught R1, so it is e to the power V input neta Vt. So we can write it like it is an antilog of V input divided by neta Vt. So if we take, so antilog of this will be equals to this. So e to the power x is there. If we take log of this, it becomes x. Okay, so similarly if we take antilog of x, it will become e to the power x. Okay, so similar is there. If e to the power V input neta Vt is there, we can represent it in terms of log, antilog. So it is like if we take the antilog of this term, it will be e to the power V input divided by neta Vt. So we can represent the output in terms of year. So you can see the input is antilog of the input terminal. So this is how we can implement the concept of antilog circuit. So this is all about the applications of operational amplifier. We have seen different applications like adder and subtractor circuit we have seen, then differentiator and integrator circuit we have seen, then multiplier. In multiplier we have seen fixed multiplier and constant gain multiplier, and also voltage follower, that is unity gain, and then log and anti-log operational amplifiers. So this is all about the applications of operational amplifiers.